Swayam Prabha. Digital India. Educated India.
To the 8th lesson of module 2, which is on analysis of strain. We have already discussed quite a few aspects of analysis of strain, and today we are going to discuss some more aspects of analysis of strain. Well, it is expected that once this particular lesson is completed, one should be able to understand the concept of strain gauges and strain rosettes, which we will be discussing as we will go through, and their use in evaluating strain and stresses at a point. One should be able to understand the relationship between elastic modulus and shear modulus. How do we relate the elastic modulus to the shear modulus, and then consequently the concept of bulk modulus. Well, hence the scope of this particular lesson includes recapitulation of previous lesson, which we will be doing through the answering of the questions which I had posed last time, then concept of strain gauges and strain rosettes, use of strain rosette values in evaluating plane strain and stresses. We will discuss that how the rosette values, the strains which we evaluate or which we measure through the use of strain rosette, how they are used to compute the values of strains and stresses at a point. Then the relation between elastic constants, and then the concept of the bulk modulus, and we will be solving few examples for evaluation of strain at a point from the given information. Well, let us look into the answers of the questions which we had posed last time. The first question is, what is the value of shear strain where normal strain is maximum? In fact, probably first and second questions both can be discussed together. What is the value of normal strain where shear strain is maximum? Now, let us discuss this particular or these two questions through the Mohr cycle or the Mohr cycle of strain. Now, if you remember, last time we had discussed that we can plot the Mohr cycle for evaluating strain at a point. Now, if we have an element which is subjected to strain, let us say this is reference x axis and this is y axis, the strain is epsilon x, epsilon y, and the shearing strain is gamma xy. Now, we can plot them in the Mohr cycle, and this is the point, this being the positive strain axis and this is the positive gamma by 2 axis. This particular point represent the positive epsilon x and gamma xy by 2, and this particular point, which is diametrically opposite to this particular point, represent epsilon y and minus gamma xy by 2. Now, this is the center of the Mohr circle, which is at a distance of epsilon x plus epsilon y by 2, and this particular point gives us the maximum normal strain, which we normally denote it as epsilon 1, the maximum principal strain. And as you can observe from this particular point and from this diagram, that at this point the value of shearing strain is 0. So, at the along the axis where the principal strain or the normal strain is maximum, where we have maximum principal strain, the value of the shear strain is 0. And consequently, if we look into the Mohr circle, that the maximum value of the strain are at this particular point and at this particular point. Now, this is the maximum positive shear strain and this is the minimum, because magnitude wise they are same, but only it is negative. So, this is gamma xy max. Now, the point where the shear strain is maximum, the corresponding normal strain is equals to this, and this normal strain is equals to epsilon x plus epsilon y by 2. So, along the axis where the shear strain is maximum, the corresponding normal strain is epsilon x plus epsilon y by 2. So, this answers the first two questions. Well, the third question is, what is the relationship between the orientation of the maximum shear strain to the orientation of maximum normal strain? Now, this aspect we had discussed last time. If you remember that the principal angle 2 theta p for the maximum principal strain can be located using the expression gamma xy by epsilon x minus epsilon y. Now, in the Mohr circle, if we try to locate the principal plane, this is the position of the maximum normal strain, and if this is the reference plane or reference point where strain is epsilon x and gamma xy by 2. Now, from this particular orientation, which is along the x direction, if we move anticlockwise by 2 theta p, we get the point of maximum strain, and in the physical space, then if we move in anticlockwise form by an angle of theta p, this gives the direction of the principal strain epsilon 1, and the expression for measuring this angle theta p, which is tan 2 theta p, is equals to gamma xy by epsilon x minus epsilon y. Consequently, we had seen that the expression for evaluating the angle for maximum shear strain, which is tan 2 theta s, is equals to epsilon x minus epsilon y by gamma xy. Now, this particular value can be written as minus 1 by tan 2 theta p, or this is nothing but equals to minus cot 2 theta p. This we can write as tan of 90 degree plus 2 theta p. Hence, 2 theta s is equals to 90 plus 2 theta p, and consequently this solution for this can be 90 plus this, if we call as theta dash, 180 degree plus theta dash will be another angle. So, the relationship between the orientation of shear strain, which is theta s, is equals to 45 degree plus theta p. That means, if we know the direction of the principal strain, from that if we orient by 45 degree, we can get the direction for the maximum shear strain. So, this is the relationship between the orientation of shear strain to the orientation of principal plane or principal strain direction, and these two directions are interrelated, and they are at 45 degree apart in the physical plane, which is at 90 degree apart in the Mohr circle of strain. Well, having looked into these questions, now let us look into the aspects which we are going to discuss today, is the concept of the strain gauge and consequently the term which is called as strain rosette. Now, many times what we need to do is that experimentally we need to measure the strain at a point in a stressed body, and that can be done using a device which we call as strain gauge. Now, electrical resistance strain gauge is one of such devices based on which or using which we can evaluate strain at a point in a stressed body. Now, the mechanism of this particular strain gauge works with its wire which is pasted on a paper base, and this assembly can be fixed onto the stressed body. Now, as the body undergoes strain or the deformation, the gauge also along with the body undergoes deformation, and thereby there is a change in the resistance of that particular wear, which is evaluated in terms of the strain. That is the basic principle. We are not going into the details of strain gauge at the moment, but the strain gauges can be used for measuring strain at a point or specifically the normal strain at a point in a particular direction. Now, this is the configuration of the strain gauge, where this particular area, which is shown over here, is the backing strip over which the wear is placed, and this is the gauge length of the strain gauge. Now, various sizes of strain gauges are available. They are ranging between 2 millimeter to even 40 to 50 millimeter size. Now, depending on the usage, depending on the type of strain we are looking for or the accuracy in the strain we are looking for, we use such gauges to measure the strain at a particular point. Now, from these particular strain values, we can, as we have seen, that we need the normal strains epsilon x, epsilon y, gamma x y, and if we have those informations, then we can compute the value of principal strains epsilon 1, epsilon 2. We can evaluate the stresses from those strains. So, measurement of strain at a point using such strain gauges is of useful aspect in strength of material. Now, let us look into that. As I said, in a plane strain we need to have three quantities. They are epsilon x, epsilon y and gamma xy, and if we can have these quantities, then we can compute the strain values which are epsilon 1, epsilon 2, the principal strains, their directions, the maximum shearing strain which is gamma xy max, and once we have the values of the principal strains, we can compute the values of principal stresses as well, which are related between the strains and the strain, they are related. So, we can evaluate what is the stress at that particular point. But the point is, the strain gauge which we use, they can be used for measuring the normal strain. The gauge can be used to measure the normal strain. Now, if we place the strain gauge along the x direction, we can get the value of epsilon x. If we place them in the y direction, we can get the value of epsilon y. But the problem is with the gamma xy, we cannot measure the shearing strain gamma xy directly, as we can measure the normal strain epsilon x and epsilon y using the strain gauges oriented in that particular direction, because strain gauge gives us the normal strain at that particular point. So, we can evaluate epsilon x and epsilon y, but measurement of gamma xy is difficult. So, we take an indirect path to evaluate gamma xy, so that we can utilize this information for evaluating principal strains and thereby the stresses. Now, the indirect path is like this. What we do is that if we install strain gauges along three directions, let us call, say, this is direction A, this is direction B and this is direction C. Now, if we place strain gauge along OA, OB and OC, then we can get the strains, the normal strain epsilon A, epsilon B and epsilon C in three normal directions or three directions. Now, let us assume that the direction OA is oriented at an angle of theta A with reference x axis, and likewise OB is oriented at an angle of theta B with reference x axis, and OC is oriented at an angle of theta C with reference x axis. Now, if we have these informations, then if you remember that we had calculated the transformation equation, which is epsilon x dash is equals to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 cos 2 theta plus gamma xy by 2 sin 2 theta. Now, this x dash direction varies with theta. Now, in this particular case, epsilon A is corresponding to theta A, epsilon B is corresponding to theta B, and epsilon C is corresponding to theta C. Now, if we substitute for theta as theta A, theta B, theta C, correspondingly we can get the values of epsilon A, epsilon B and epsilon C, and this is what is done over here is epsilon A is equals to epsilon x plus epsilon y by 2, epsilon x minus epsilon y by 2 cos 2 theta A plus gamma xy by 2 sin 2 theta A. Likewise, epsilon B is equals to epsilon x plus epsilon y by 2, epsilon x minus epsilon y by 2 cos 2 theta B and gamma xy by 2 sin 2 theta B, and epsilon C likewise is cos 2 theta C and sin 2 theta C. Now, you see we have three equations, equation 1, equation 2 and equation 3, and out of these three equations we know the value of epsilon A, we know the value of epsilon B, we know the value of epsilon C. Also, we know the orientation angle theta A, theta B and theta C. Since these three parameters or 6 parameters are known, epsilon A, epsilon B, epsilon C are known, consequently theta A, theta B, theta C are known. So, the unknown parameters epsilon x, epsilon y and gamma xy can be evaluated from these three equations. So, we can compute epsilon x, we can compute epsilon y and we can compute gamma xy from these equations. So, once we know epsilon x, epsilon y and gamma xy, then using these three quantities we can evaluate strain at any orientation as we desire, as we have seen, either using transformation equation or using Mohr circle, or we can evaluate even the principal strains and consequently we can evaluate principal stresses from the material properties. Well, then when we use the strain gauges together to measure the strain at a particular point, we call that assembly as the strain rosette. The formation of three gauges together is termed as strain rosette. Now, these angles which I had shown as theta A, theta B and theta C, they can be chosen according to our own convenience, and normally used angles are the 45 degree or 60 degree. Now, this is called as a 45 degree strain rosette. Now, here two angles used are, let us call this as theta A is 45 degree and theta B is 45 degree again. Now, along x direction we have oriented A, along 45 degree we have B, along 90 degree we have C. So, since epsilon A or the strain along the A is coinciding with x axis, so epsilon x is epsilon A directly. Likewise, since this particular gauge C is oriented in the direction of y, the epsilon y is equals to epsilon C. So, directly we can get the value of epsilon x and epsilon y from the measured strain value of epsilon A and epsilon B. Now, what we need to do is evaluation of gamma xy. Now, again if we go back to the transformation equation, which is epsilon x dashed is equals to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 cos 2 theta plus gamma xy by 2 sin 2 theta. Now, theta here is 45 degree. So, sin 90 is 1, cos 90 is 0. So, this term goes off, and this is gamma xy by 2, and this is in direction of 45 degree, which is epsilon b. So, epsilon b is equals to epsilon x is epsilon A plus epsilon y is epsilon c. So, epsilon A plus epsilon c by 2 plus gamma xy by 2. So, from this it gives gamma xy by 2 is equals to epsilon b minus epsilon A plus epsilon c by 2. So, we get the value of epsilon x, epsilon y and gamma xy from the measurement of this particular type of strain rho z, and which can be utilized for evaluating the strain or the principal strain at that particular point, and those principal strains can be utilized for evaluating stresses at that particular point. Now, another kind of strain rho z is which are oriented at an angle of 60 degree. Again, the whole assembly, the whole 3 strain gauges fixed in this particular form can be fixed on the surface where we like to measure the strains, and mind that at that particular point we are measuring strains in 3 different directions which are oriented at an angle of 60 degree with reference to the reference x axis. Now, this is reference x axis, and here now the y axis is in this direction. So, let us call this as direction A, this as B and this as C. So, as usual, since the strain in the gauge A is in the x direction, so epsilon x will give us directly epsilon A. Now, here neither the gauge is oriented in the direction y, so epsilon y we cannot get directly, and we cannot evaluate the value of gamma xy directly as we have seen earlier. So, we will have to find out the values of epsilon y and gamma xy from the measured strain of in the direction of B and C, and to evaluate the strain value at epsilon y and gamma xy, we make use of the transformation equation, which is again epsilon x dash is equals to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 cos 2 theta plus gamma xy by 2 sin 2 theta. Now, when we substitute for B, that means epsilon B is equals to epsilon x plus epsilon y. Now, epsilon x is already epsilon A by 2 plus epsilon A minus epsilon y by 2 cos 2 theta, theta being 60 degree, this is cos 120 degrees plus gamma xy by 2 sin 120 degree. Now, likewise, we evaluate the strain in the C direction, which is epsilon C, which is equals to again epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2. Now, theta here is 120 degree. So, cos 240 degree and sin 240 degree, and once we substitute the values of that, then we get 2 equations in epsilon B and epsilon C, and we have 2 unknown parameters epsilon y and gamma xy, and these 2 can be solved, and if we solve that, we will get the values of epsilon y and gamma xy in terms of epsilon B and epsilon C. So, we have again 3 quantities epsilon x, epsilon y and gamma xy in terms of epsilon A, epsilon B and epsilon C, and that was what our objective is, to find out the values of epsilon x, epsilon y and gamma xy in terms of epsilon A, epsilon B and epsilon C, and these are the 3 normal strains which we have measured at a point, based on which we can compute other quantities as we desire. Well, now this is another important aspect wherein we need to relate the quantity which is E, which we call as modulus of elasticity, to the quantity G, which we call as the modulus of rigidity, and this we have seen the definition of E and G earlier. Now, we like to relate here these 2 quantities E and G. Now, let us look into a state of stress at a point where the stresses are all shearing stresses acting in the at that particular point in this element. Now, here the normal stresses sigma x and sigma y is equals to 0, and the shearing stresses are tau x y. Now, if you remember that this kind of stress distribution, we call that state of pure shear, and this aspect we have discussed earlier when we discussed about the stress at any point. So, this is a state of pure shear. Now, if we try to plot this stress in the Mohr circle, as we have seen that this is our sigma axis and this is our tau axis. Now, on this this particular plane, your sigma, the normal stress, is equals to 0, and we have only positive tau xy, which is causing anti-clockwise moment, and correspondingly if we place here, now here sigma, this is sigma axis, sigma is 0, and we have positive tau. So, this is the point which can be represented of this particular stress value, and perpendicular direction again sigma y is 0. So, we have normal stress 0 and negative of tau, which is this particular point. So, considering this as center, let us call O as a center and OA or OA dashed as the radius. If we draw the circle, this gives us the Mohs circle of stress corresponding to the pure state of shear at a particular point. Now, in this diagram, this is the maximum normal stress, which we call as sigma 1, and this is the minimum normal stress, which we call as sigma 2. And please observe that the maximum stress point O dashed or the minimum stress point O double dashed, they are of same magnitude, which is equals to the radius of this circle, and radius of this circle is equals to tau xy. So, sigma 1 is equals to tau xy and sigma 2 is equals to minus tau xy, and this is the element where the principal stresses sigma 1 and sigma 2 are acting. Now, this aspect must be noted, which we have seen consequently when we were evaluating the direction for the principal strain. We had seen that the direction of principal stress at a point and direction of principal strain, they match. In fact, they are oriented at an angle of 45 degree with reference to the reference x axis. Hence, the principal strain and the principal stresses occur in the same direction. This is quite important. Now, we know that in this particular point, if we like to find out the strain epsilon 1, we can compute that epsilon 1 as equals to sigma 1 by E minus mu times sigma 2 by E. This is the plane state of stress that is acting in this sigma 1 and sigma 2, and if we like to evaluate the strain, sigma 1 by E is the direct strain, and this is because of the Poisson effect. So, epsilon 1 is equals to sigma 1 by E minus mu sigma 2 by E. Now, if we substitute for the value of sigma 1 and sigma 2, so we have epsilon 1 is equals to sigma 1 by E minus mu sigma 2 by E, and as we have seen that sigma 1 is tau xy and sigma 2 is minus tau xy. Hence, epsilon 1 is equals to tau xy by E minus mu times minus tau xy by E. So, this is equals to 1 plus mu tau xy by E. Let us call this is equation 1. Now, we have seen that the strain at any direction epsilon x dash is equals to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 cos 2 theta plus gamma xy by 2 sin 2 theta. Now, since the direction of principal stress coincides with the direction of principal strain, and also we have noted that sigma x is equals to sigma y equals to 0. So, since normal stresses are 0, corresponding normal strains are also 0, epsilon x is equals to 0, epsilon y also is equals to 0. Hence, the first term is 0. Now, since the direction of the principal strain also is theta as equals to 45 degree, then cos 90 is 0 and thereby sin 90 is 1. So, epsilon 1, the strain in the principal direction, is equals to gamma xy by 2. Now, the relation between the stress and the strain, the shearing stress and the shearing strain, can be related through the shear modulus using the Hooke's law. So, tau xy is equals to g times gamma xy. So, you can write tau xy, the shearing stress, is equals to G times gamma xy, where G is the shear modulus. Now, gamma xy you can substitute in terms of tau xy as equals to tau xy by twice G. So, this is our second equation. So, first equation we have epsilon 1 is equals to 1 plus mu tau xy by E, and the second equation which we have is epsilon 1 is equals to tau xy by 2 G. Now, if we equate these two, in the first place we have 1 plus mu tau xy by E is equals to tau xy by twice G. Hence, we can write that tau xy gets cancelled. So, is G is equals to E divided by 2 into 1 plus mu. So, this is the relationship between the shear modulus G and the elastic modulus E through the term Poisson's ratio. So, this is the relationship between E, G and mu. Now, please note that though these are the three quantities E, G and mu, these three elastic constants which are necessary for evaluating deformation at a particular point, but out of these three quantities, two are independent and one can be evaluated in terms of the other two. Now, this is the expressions which we have just derived, is written over here. Epsilon 1 is equals to 1 plus mu tau xy by E, and then epsilon x dashed is equals to epsilon x plus epsilon y by 2, epsilon x minus epsilon y cos 2 theta by 2, which we have seen right now. And for epsilon x, epsilon y equals to 0 and 2 theta equals to 90 degree, if we relate these two, we have G equals to E divided by 2 into 1 plus mu. So, this is the relationship between E and G through the term Poisson's ratio. Mu is the Poisson's ratio. Well, let us look into another quantity which we define as bulk modulus. Many times we need to know the volume change in at a particular stressed body, and if we try to find out, we generally come up with another constant k, which we call as the bulk modulus, which is related to the change in the volume in a stressed body. Now, let us look into at a point a small body which is having a dimension dx, dy and dz. Let us say this is dx, dy and dz is the elemental length. So, the volume of this particular small element is equals to dx times dy times dz. Now, after this particular element has undergone strain, there will be extension in all three directions, and thereby there will be change in the volume. Let us say that the strains in the x, y and z direction are epsilon x, epsilon y and epsilon z, and thereby the extension in the x direction will be epsilon x times dx, the extension in the y direction will be epsilon y times dy, and extension in the z direction will be epsilon z times dz. So, the changed volume accordingly will be equals to, let us call this as V dash, as dx plus epsilon x dx is the changed length in the x direction, dy plus epsilon y dy is the changed length in the y direction, multiplied by dz plus epsilon z dz, or this we can write as dx dy dz. If we take out dx dy dz, we have 1 plus epsilon x into 1 plus epsilon y into 1 plus epsilon z. If we expand this is equals, now dx dy dz as we have seen is the initial volume which is V0 times, if we expand this is 1 plus epsilon x plus epsilon y plus epsilon z plus epsilon x epsilon y plus epsilon y epsilon z plus epsilon x epsilon z plus epsilon x epsilon y epsilon z. This is the expression which we are going to get if we multiply these three quantities. Now, since the strain is small, epsilon x, epsilon y, epsilon z, they are small quantities. So, the product of these quantities epsilon x, epsilon y and epsilon x, epsilon z and epsilon y, epsilon z and epsilon x, epsilon y, epsilon z, we consider them as 0 or insignificant. So, this is equals to V 0 into 1 plus epsilon x plus epsilon y plus epsilon z, and this B dashed minus V 0 by V 0 is equals to then epsilon x plus epsilon y plus epsilon z. Now, V dash minus V 0 is the change in the volume delta V. Now, delta V by V 0 is epsilon x plus epsilon y plus epsilon z, and this we denote by quantity E. And in fact, this is known as dilatation, that change in volume per unit. If V 0 is unit, then change in volume delta V gives E. So, dilatation is a quantity which is called as the change in volume per unit volume, and which is represented in terms of strain as epsilon x plus epsilon y plus epsilon z. Now, we know the relationship between the stress and the strain is epsilon x is equals to sigma x by E minus mu times sigma y plus sigma z by E. Likewise, epsilon y is equals to sigma y by E minus mu sigma x plus sigma z by E. This we have seen while discussing the generalized Hooke's law, and epsilon z is equals to sigma z by E minus mu sigma x plus sigma y by E. Now, if we add together, epsilon is E is equals to epsilon x plus epsilon y plus epsilon z, as we have seen, and this is equals to in terms of stresses as sigma x plus sigma y plus sigma z by E minus twice mu times sigma x plus sigma y plus sigma z, this divided by E, and this is equals to 1 minus twice mu by E times sigma x plus sigma y plus sigma z. So, E is equals to 1, E is related to the stress as equals to 1 minus twice mu by E times sigma x plus sigma y plus sigma z. Now, if we take that small body from which we have evaluated this quantity, now if we say that the stresses which is acting on this particular body sigma x, sigma y and sigma z, if they are all of magnitude p and acting in the compressive direction on all sides, this is we call as a state of hydrostatic pressure. That means, a body is subjected to pressure from all directions. So, thereby the sigma x, sigma y and sigma z are of equal value and they are of magnitude p, and this particular state of stress in a body we call as a state of hydrostatic pressure. Now, if we replace the value of sigma x, sigma y, sigma z in terms of p, then since it is acting in the compressive direction they are minus. So, sigma x is minus p, sigma y is minus p, sigma z is minus p. So, this is equals to minus E is equals to minus 3 p by E into 1 minus twice mu, and this is the quantity minus p by E. If we write minus p by E, this is equals to E by 3 into 1 minus 2 mu, and this particular quantity minus p by E is normally designated as the bulk modulus K. So, K is related to this elastic modulus E and Poisson's ratio mu as K equals to E times 3 by 1 minus twice mu, and this is what has been discussed here. If you look into that, these are the expressions as we have derived right now, that epsilon is equals to epsilon x plus epsilon y plus epsilon z, and E is equals to consequently 1 minus twice mu times sigma x plus sigma y plus sigma z by E, and E is equals to minus 3 times 1 minus 2 mu p by E when the element is subjected to the state of hydrostatic pressure, that in all direction it is subjected to P. These are all P, and because of this the state of stress sigma x plus sigma y plus sigma z is minus 3 P. This gives us the expression E equals to this, and thereby minus P by E, this quantity we call as bulk modulus, and the bulk modulus value is equals to E divided by 3 into 1 minus twice mu. And this term is important, as I defined that dilatation, which is the change in volume for unit volume for a small infinitesimal strain, which is given by this expression E. Well, let us look into this example problem. Now, after looking into the aspects of strains, we have discussed through transformation equations, through Mohr-Circle, and also we have seen usage of strain gauges and the strain rosettes, from which we can find out the values of strains, normal strains in different directions, which can be utilized for the evaluation of normal principal strain at a particular point, from which we can compute the values of principal stresses. Now, let us look into the example. Last time I had solved one example, and I had given this example to solve for using the Mohr-Circle of strain. Now, the values of epsilon x is given as this, epsilon y is this, and gamma xy as this. So, what you need to do is to compute the values of the principal strain and their directions, direction of principal strain, and also the maximum shearing strain based on these data using Mohr-Circle of strain, and we will have to find out the strains at a direction which is oriented at 30 degree in an anticlockwise direction with reference to the x axis. Now, let us plot the Mohr-Circle, and then it will be clearer that how we can solve this particular problem. Now, given values are epsilon x is equals to 340 into 10 to the power minus 6, epsilon y is equals to 110 into 10 to the power minus 6, and gamma xy is equals to 180 into 10 to the power minus 6. Now, if we plot this in the Mohr-Circle, let us say this is the gamma by 2 direction, this is epsilon direction, this is gamma by 2 direction. Now, here we have epsilon x 340 and gamma by 2 is 90. So, this is the point which we choose here. We have another point epsilon y which is 110 and gamma by 2 is minus 90. So, we place the point here, and as per the norm of the Mohr-Circle we join these 2 points, and thereby this gives us the center of the Mohr-Circle. And if we plot the circle considering this as center and this as radius, we get the circle. Now, this particular point gives us the point of maximum normal strain, which we define as epsilon 1, and this is the minimum normal strain which we define as epsilon 2. Now, in this figure, if you remember the center from here, now this is epsilon x, this is epsilon y, hence this is epsilon x minus epsilon y by 2, and thereby this distance is epsilon x plus epsilon y by 2. Now, the values of these if we calculate epsilon x plus epsilon y by 2, epsilon x plus epsilon y by 2 is equals to 340 plus 110, 450 means 225 into 10 to the power minus 6. I am keeping 10 to the power minus 6 silent for the time being, and then epsilon x minus epsilon y by 2, this is equals to 230 by 2, which is 115. Now, normal strain epsilon 1 will be the distance from O to O dash plus the radius, and the radius can be computed from this triangular configuration, where let us call this as A, this is A dash. Now, A dash is equals to gamma by 2, which is 90 into 10 to the power minus 6, and this distance is epsilon x minus epsilon y by 2, which is 115. So, the radius r is equals to root of 90 into 10 to the power minus 6 square plus 115 square, and this gives us a value of 146 into 10 to the power minus 6. Now, these quantities are with 10 to the power minus 6, which I am keeping silent here. So, r is equals to 146 into 10 to the power minus 6. So, the value of normal strain, maximum normal strain epsilon 1 is equals to O dash plus O dash plus the radius r, and O dash is equals to epsilon x plus epsilon y by 2, which is equals to 225. So, 225 plus 146, this gives us the value of the normal strain maximum, which is 371. 371 into 10 to the power minus 6 is the normal strain, maximum normal strain, and the minimum normal strain epsilon 2 is equals to this particular distance, again is the distance from O to O dash minus the radius. So, O dash again is 225 minus radius is 146 into 10 to the power minus 6. This gives us a value of 79 into 10 to the power minus 6. So, these are the values of the maximum normal and the minimum normal, the principal strains. Now, we need to know the orientation of the principal strain, and this is the reference x axis where the normal epsilon x and gamma xy by 2 positive occurs. Now, from here if we rotate by angle 2 theta p, this gives us the position of the maximum normal strain, and from this particular triangle O dash A dash, we can get tan 2 theta p, tan 2 theta p is equals to A dash by O dash A dash, A dash by O dash A dash, and that gives us a value of which is A dash is equals to 90 and O dash A is equals to 115. So, 90 by 115 tan inverse of that gives us the value of 38 degree, 230 p, 2 theta p is equals to 38 degree, and thereby theta p is equals to 19 degree. So, this is the orientation along which the maximum principal strain occurs. Now, what we need to do is to evaluate the strains at a direction which is oriented at an angle of 30 degree with reference to the reference x axis. So, if it is oriented at an angle of 30 degree in the Morse plane, it is twice the theta. So, it is 60 degree. Now, with reference to the positive epsilon x and gamma xy by 2, if we orient by 60 degree, so this is the 60 degree point, and if we join the line from center to this, we get this particular point, which is the direction where we need the strains, and this will give us the value of, this is the normal strain and this is the value of the shearing strain by 2, gamma x dash y dash by 2. Now, this particular angle is 38 degree, so, and this total angle is 60 degree. So, 60 minus 38, this is, if we call this as alpha, alpha is equals to 22 degree. Now, if we can compute the value of A and this distance B, then we can find out the normal stress, which is O dash plus B, and shearing strength is gamma xy by 2 or x dash y dash by 2 is equals to A, or which is minus A, it is negative in the Morse plane. So, if we compute those two value, now this is the radius, r cos of alpha will give us this particular distance and r sin of alpha will give us value A. So, once we know the value of A and B, we can compute epsilon x and gamma x dash y dash. Now, let us compute that the values of A and B. Now, A is equals to r sin 22 degree, which is equals to 146 into 10 to the power minus 6 into sin 22 degree, and this gives us a value of minus 54.7 into 10 to the power minus 6. I am writing this as a minus because it is in the negative direction. So, gamma x dashed y dashed, in fact the shearing strength is twice of this. So, minus 109.4 into 10 to the power minus 6 is the shearing strain. Now, the distance B is equals to r cos 22 degrees, which is equals to 146 into 10 to the power minus 6 cosine 22 degree, and this is equals to 135.37 into 10 to the power minus 6. So, epsilon x dashed is equals to the O dash distance, which is equals to 225. So, 225 plus 135.37 into 10 to the power minus 6 is the normal strain, and epsilon y dash consequently will be this minus of this, which is diametrically opposite, is equals to 89.65 into 10 to the power minus 6, and gamma xy, as I said, is equals to this. So, these are the values of the strain, and maximum shear strain is equals to the radius of the Morse circle. Maximum shear strain is equals to 2 into 146, because gamma by 2 is the radius. So, 2 into 146 into 10 to the power minus 6, which is 292 into 10 to the power minus 6. So, these are the values of the strain quantities. Now, once this particular element undergoes strains, now this is the configuration which we expect. Now, in the initial stages, we had epsilon x as 340, epsilon y as 110, and we had positive shear, which is denoted by this as 180, and this is the orientation of the element in initial strain. Finally, when it is rotated at an angle of 30 degree, now it has epsilon x dash, epsilon y dash, and gamma x dash y dash is negative. So, the angle here increases, and this is the form which it takes, and so this is the final shape of the body after it has undergone the strain. And when it undergoes the principal strain, the principal strain direction is we have got as 19 degree. So, this is the direction of epsilon 1 and this is the direction of epsilon 2, and both are positive, and this here there are no shearing strain. So, this is the shape that it is going to take place. Well, we have another example which is of similar type, that an element of material in plane strain is subjected to strains epsilon x as 480 into 10 to the power minus 6, epsilon y as 70 into 10 to the power minus 6, gamma xy is 420 into 10 to the power minus 6. We will have to evaluate the strain at an element which is oriented at an angle of 75 degree with x axis in anti-clockwise direction, and the principal strains and maximum shear strain using Morse circle. This is exactly the similar way you should do as we have done for the problem 1, and I am leaving this for you to compute. Now, the another example wherein this is also identical, we have epsilon x, epsilon y and gamma xy. The strains at a point for an element of material in plane strain are of this form, where epsilon x is 120 into 10 to the power minus 6, which is positive, epsilon y is negative, is minus 450 into 10 to the power minus 6, and the shearing strain also is negative, negative 360 into 10 to the power minus 6. We will have to determine the principal strains and the maximum shear strain. Now, using Mohs circle of strain. Now, this is also being similar to the previous problem. I am leaving this for you to solve. Now, let us look into this particular problem, which is based on the aspects we have discussed today, where the strain readings from a 45-degree strain rosette are epsilon A is this much, epsilon B is this much, and epsilon C is this much. If E is equals to this and mu is this, what will be the values of the principal stresses? Now, as you have seen that we have rosettes which are oriented in 3 different directions. This is epsilon A, this is epsilon B, and this is epsilon C. And as we have seen that epsilon x is equals to epsilon A, epsilon y is epsilon C, and gamma xy by 2 thereby is equals to epsilon B minus epsilon A plus epsilon C by 2. Now, from this we can get the values of epsilon x, epsilon y, and gamma xy, and we can compute the values of the stresses. Now, the values of epsilon A is equals to 300 into 10 to the power minus 6, epsilon B is equals to 600 into 10 to the power minus 6, and epsilon C is 100 into 10 to the power minus 6. Now, epsilon or gamma xy by 2 thereby is equals to 600 minus 300 plus 100 by 2 into 10 to the power minus 6, which is 400 into 10 to the power minus 6. Now, if we plot these in a Mohs circle with the values of epsilon x, and epsilon A is epsilon x and epsilon C is epsilon y. Now, this if we plot in the Mohs circle, this is the epsilon axis and this is the gamma by 2 axis. We have epsilon x as 300 and gamma xy by 2 is plus 400. We have epsilon y as 100 and gamma by 2 as 400, and if we join these two together we get the center, and if we plot the circle, we get the Mohs circle of strain, and this is the value which is sigma or epsilon 1, and this is epsilon 2. Now, this distance is equals to epsilon x plus epsilon y by 2, which is 300 plus 100, 400 by 2 is equals to 200, and this distance epsilon x minus epsilon y by 2, which is 200 minus 100, which is 100, 300 minus 100 is 200 by 2 is 100, and this distance is 400. So, r is equals to root of 100 square plus 400 square into 10 to the power minus 6 we have, and this is equals to 412.3 into 10 to the power minus 6. Hence, the value of epsilon 1 is equals to this distance plus the radius, and this distance is equals to 200. So, 200 plus 412. So, this gives us a value of 612, and consequently epsilon 2 is this distance minus the radius. So, this is negative, which is 200 minus 412 into 10 to the power 6 or 10 to the power minus 6, which is equals to minus 212 into 10 to the power minus 6. So, that is the value of epsilon 2. So, once we have this value of epsilon 1 and epsilon 2, now as you know, the value of epsilon 1 is equals to sigma 1 by E minus mu times sigma 2 by E, and consequently epsilon 2 is sigma 2 by E minus mu sigma 1 by E. Now from this, if we substitute value of epsilon 1 and 2, we can get the value of sigma 1 and sigma 2. Well, to summarize then, in this particular lesson we have included the concept of strain gauges and strain roses and some of the relationship between the elastic moduli, and these are the questions set for you. Well, the answers for, well, thank you very much for your attention.